Welcome to this session entitled Introduction to Oracle's Python Technologies. My name is Mark Hornick, and I'm a director in the Advanced Analytics and Machine Learning group. Today we're going to look at what Oracle is doing with Python relative to Oracle Database, and in particular, its support for machine learning. This is Oracle's standard safe harbor statement, indicating the content I'll be discussing is intended to outline our general product direction. Note that the component, Oracle Machine Learning for Python, has not been released yet as of this date. For our agenda today, we're going to start with a brief overview of what Python is, then survey Oracle's overall advanced analytics offerings. Next, we'll look at the database connectivity package, CX Oracle, and the new component that is about to be released, Oracle Machine Learning for Python. So let's begin with what is Python. Python has been around for decades and serves as an interpreted, object-oriented, high-level general-purpose programming language that's designed for rapid application development and scripting. As an open-source scripting language and environment that is being taught widely in universities, Python has become a favorite tool for data scientists. It has a rich ecosystem of package contributors and users, with thousands of open-source packages to enhance user productivity. Although it's open source, Python's licensing makes it freely usable and distributable, even for commercial use. Which language is the most popular? Well, it depends on who you ask and for what purpose. This plot takes a look at the relative popularity of major programming languages. It plots counts of Stack Overflow questions that are raised for each of these programming languages over time, starting back in 2009. We can interpret number of questions as being correlated with the interest in the language. What is clearly evident is that Python since 2012 has had a steady increase in interest. In contrast, languages such as C#, PHP, and even Java and JavaScript have seen declines, C# being the most notable. So why should we use Python? What is in Python that attracts so many users? Some claim it's a simple language. Python has strict punctuation rules and uniform code formatting that makes it easy for programmers to work with each other's code. Python has many third-party libraries, and looking at PyPy, there are over 168,000 projects. Python is also heavily used for websites. Perhaps most telling is the rise of Python among data scientists, with the rich set of data preparation capabilities and machine learning algorithms available. Python users also have a wide range of integrated development environments, or IDEs, available, including Spider, Rodeo, PyCharm, and Jupyter, among others. The Rodeo IDE is similar to the RStudio IDE for R. The Jupyter Notebook environment is very popular among data scientists since it allows documenting one's work in place with the code and the results. So now let's turn our attention to Oracle's advanced analytics technologies. For advanced analytics, Oracle provides multiple interfaces across multiple platforms. Whether your preference is SQL, R, Python, or a graphical user interface, you can work with Oracle's advanced analytics tools. R and Python programmers can use their favorite IDEs to program directly in those languages against data stored in, for example, Oracle Database. Data and business analysts can use the drag-and-drop GUI available through Oracle Data Miner, which is part of SQL Developer. Business analysts and managers may prefer dashboards, and domain end users can simply reap the benefits of advanced analytics and machine learning through prepackaged applications. Due to their tight integration with SQL, these tools can be used in combination with dashboarding tools like Oracle Data Visualization or Oracle Analytics Cloud, and domain-specific applications such as HCM. Looking at the platform level, on the left we have a big data tool referred to as Oracle R Advanced Analytics for Hadoop, which is part of the Big Data Connectors software suite. It provides parallel distributed Spark-based algorithms for manipulating big data. On the right, we show Oracle Database Enterprise Edition with the Oracle Advanced Analytics Database option. It's with this option that you get access to SQL, R, and Python integration for scalable, distributed, parallel in-database machine learning execution. And of course, this functionality is also available on the Oracle Cloud. So what are the differentiators with Oracle Advanced Analytics? The first is that users can work directly with data, whether in Oracle Database or Hadoop. This allows data scientists to get at the data they need without having to make requests from IT or their database administrator to provide extracts, perhaps as flat files. But more importantly, it allows them to process data where they reside, which minimizes or eliminates data movement. This can be a significant time savings, especially when larger data volumes are involved. The next is scalability and performance. Data scientists can use parallel distributed algorithms that can fully leverage powerful engineered systems supporting the database. So whether they are building models on billions of rows of data or millions of models in parallel, they're able to take better advantage of their hardware, processing bigger data faster. The ability to put your results in production quickly and easily is also a major differentiator. This ease of deployment allows users to immediately place their Python, R, and SQL scripts into production with no need to recode. In addition, they can take advantage of production quality infrastructure and avoid custom plumbing and the associated extra complexity in testing that is required. The in-database script repositories make it easy to hand off data scientists' work products to application developers. Lastly, there's process support. For example, with Oracle Database, you will likely already have procedures for data security, backup, and recovery in place. Using the Oracle Advanced Analytics option to Oracle Database allows you to immediately take advantage of those existing processes. In addition, the various analytics objects, such as models, scripts, workflows, and of course data, can be stored, accessed, and managed within Oracle Database. At this point, let's switch to Oracle's Python technologies, in particular those that support Oracle Database. Those are the CX Oracle package and the new Oracle Machine Learning for Python. Note that as a component of the Oracle Advanced Analytics option to Oracle Database, Oracle Machine Learning for Python is available to customers already licensed for Oracle Advanced Analytics. So what is CX Oracle? It's a Python package that enables scalable and performant connectivity to Oracle Database. This package is available as open source, and Oracle is the maintainer. As the Oracle-provided interface for Python to Oracle Database, it's optimized for performance with Oracle Database, being based on OCI. With CX Oracle, users can execute SQL statements from Python. This is important to enable transactional behavior for standard SQL statements involving insert, update, and delete. We introduced CX Oracle since it is the package used for communication between Oracle Machine Learning for Python clients and the Oracle Database. As noted for transactional behavior, users may choose to use CX Oracle directly or in combination with Oracle Machine Learning for Python to get that transactional behavior. Let's take a quick look at some code. We first import the package CX Oracle and then connect using a variety of connect strings and arguments. We can print out the version of the database we're connecting to and close connections as well. Once we have a connection, we can open a cursor, which allows us to invoke SQL statements. We can access the results in the cursor, whether to print all the data, return a single row as a tuple and advance to the next row, or return a set of rows. Closing the cursor and connection frees any temporary resources. Now let's turn our attention to Oracle Machine Learning for Python, which goes by the acronym OML4Py. One way of getting data from a database into a Python engine is to make a request from a database administrator for a data extract, perhaps as a flat file. And when the results are produced, those can be sent back to the database administrator to load into the database. Of course, this is extremely inefficient. Programmatic interfaces also exist, including CX Oracle, to allow programmers to directly log into a database and retrieve the data they need and put results back. When trying to put a Python-based solution in production, some may turn to ad hoc approaches such as cron jobs that start the Python engine, extract the data, send results back to the database, etc. This introduces data access latency. That is the time it takes to pull the data out of the database and push results back. And just as the size of the data increases access latency, it can also run into Python engine memory limitations, which affect how much data can actually be processed at one time. Most Python code and packages are single-threaded. To take advantage of multiple processors or cores, special coding is often required. In addition, having to shift from one language to another, such as from Python to SQL, introduces a paradigm shift which can be problematic for users not familiar with SQL. With ad hoc production deployment, there can be a great deal of replicated functionality across projects, and increased testing for complex failure scenarios are required. And we've already talked about backup recovery and security. So this is where OML4Py comes in. Oracle Machine Learning for Python, as an Oracle Advanced Analytics component, runs on Oracle Database 18c or greater. It uses Oracle Database as a high-performance compute environment, where the database performs the heavy lifting. Data scientists can use powerful in-database parallel and distributed machine learning algorithms. They can manage their Python scripts and Python objects in the database and invoke them at the database server side. We'll say more about that shortly. To facilitate production deployment, Python results can be integrated into applications and dashboards through SQL invocation, which is natural for many applications and dashboarding tools. Lastly, Oracle Machine Learning for Python allows data scientists to produce better models faster, with a new feature referred to as automated machine learning, or AutoML. Going to the next level of detail, we can characterize the functionality of Oracle Machine Learning for Python as being in 4 areas: the transparency layer, parallel distributed algorithms, embedded Python execution, and automated machine learning. The transparency layer leverages proxy objects so that data scientists use standard Python syntax and invoke overloaded Python functions that get translated into SQL for in-database execution. This allows users to take advantage of the scalability and performance of Oracle Database by leveraging query optimization, column indexes, table partitioning, and more significant server machine resources such as RAM and CPU. The parallel and distributed algorithms are exposed through a Python API and correspond to the in-database algorithms from Oracle Data Mining. By being implemented in the kernel of the database, these algorithms have no need to move data from the database and are implemented with scalability and performance in mind. Embedded Python execution allows users to take their Python scripts in the form of user-defined functions and execute them individually, or to leverage parallelism by partitioning data for data parallel execution, or task parallel execution for tasks like Monte Carlo simulation. With embedded Python execution, users can leverage the vast array of open source Python packages by having them installed on the database server machine. While the features mentioned so far are also present in Oracle R Enterprise, a new capability with Oracle Machine Learning for Python is automated machine learning, which provides automated feature selection, model selection, and hyperparameter tuning. We'll say more about those later. For the moment, let's take a closer look at the transparency layer. This leverages proxy objects for database data such as tables and views. If we have a pandas data frame that contained, for example, Boston housing data, we can create a persistent table named Boston. This returns a proxy object that we could use in subsequent function invocations. If the Boston table already exists, we can use the function sync to get a proxy object. There are a variety of overloaded functions that translate the requested function into SQL for execution in database, while maintaining similar Python syntax for the user. On the right are a couple of examples of overloaded functions that could be invoked on the data proxy object. Here's a list of data transfer related functions. We've already seen the create function for creating a persistent table from a pandas data frame. We can also create a temporary table using the push function. To get a proxy object on existing tables, we use the sync, as we saw before. We can also drop tables, list the set of proxy objects that exist in the workspace, and even get a cursor object from the connection that can be used for invoking SQL explicitly from the CX Oracle API. To get a feel for the range of functions that are overloaded, here's a list. We'll take a look at a couple of these next. Just to set up the example, let's create a data frame with 4 columns: gender, hand, which is left or right, speed, and accuracy. First, we'll create a temporary table and get back a proxy object by using the push function. We see that X is the OML data frame. From here, we can compute a cross-tabulation to find the categories that the most entries belong to and sort those values by descending count. We see that the result is also an OML data frame. This ensures that if you have a large result, you don't pay the overhead of pulling data to the client unless you actually want or need it. In another example, we use pivot to find the ratio of entries with different hand values for each gender value and across all entries. Let's move on to the set of in-database machine learning algorithms that are exposed in Oracle Machine Learning for Python 1.0. Here you see a rich set of classification algorithms, regression algorithms, and others supporting clustering, market basket analysis, attribute importance, feature extraction, and anomaly detection. While this doesn't reflect every algorithm that's currently available as part of the Oracle Advanced Analytics option, we'll be adding additional algorithms in future releases. Note that the Python API enables users to leverage partitioned models and text mining in combination with these algorithms, just as you can with Oracle R Enterprise and the Oracle Data Mining SQL interface. Because no suite of algorithms is ever complete or contains every algorithm that data scientists would want to use, these can be supplemented with open source Python packages and used with embedded Python execution. While the open source packages likely will not scale, you still have the ability to leverage data parallel and task parallel execution of your Python scripts with embedded Python execution. Let's walk through a few other code examples relative to embedded Python execution. Here again, we connect to the database and test if we're connected. To invoke a user-defined Python function from a client Python engine, we first define that function. Here we call it fit, which builds a linear support vector machine classification model and returns it and takes a data frame as argument. We load that function into the Python script repository in the database and give it the name sk_svc_fit. Then we list the scripts that are in the script repository. Finally, we use the function tableApply, specifying the training data, the name of the function we wish to invoke, and that the input data type is a pandas data frame. Alternatively, the input data type could be a NumPy rec array. The model is returned from the tableApply function. Behind the scenes, a Python engine is spawned, the user-defined function is loaded into that engine, and is invoked with the data specified for the first argument of the tableApply function. In this next example, we define a function buildLM that predicts petal length, giving petal width, and returns the linear model. This is based on the iris dataset. Because we're illustrating group_apply, we specify an index, which is the column or columns that the data should be partitioned on. The user-defined function is then invoked on each partition, and each model returned in the result. To see the individual models, we pull them back to the client, since they remain at the database server until requested as serialized objects. Here is the full set of functions that are available for embedded Python execution in OML4Py. You can just invoke the user-defined function, passing no data to it using doeval. You can pass all of the data in a table into your function using tableApply. You can ask for chunks of data to be fed to multiple invocations of your function in parallel using rowApply, which can be useful for scoring in parallel. You can partition your data and feed each partition to your function in parallel using group_apply. This can be useful for building multiple models, for example, one per customer. Lastly, you have the ability to invoke your function multiple times in parallel without providing database table data through an argument. Of course, you can pass arguments to your function in general. In the Python interface, you can pass both scalar and non-scalar objects. However, in the SQL interface, you can only pass scalar objects. We showed earlier how you could create a script in the Python script repository. These are the set of functions that allow you to do that, as well as list the scripts in the repository, load scripts into memory so that they can be invoked, as well as to drop scripts. Earlier, we talked about saving Python objects in the Oracle database. We do this through a feature we referred to as data store. Users can save one or more objects in a named data store. They can list the existing data stores that are available to the current session user, as well as inspect the contents of the data store. They can load the Python objects in the data store into memory, and of course delete data stores or objects within a data store. There's also the ability to grant and revoke access to other users of your data store. So let's move on to the last piece of functionality that we'll cover, which is automated machine learning, or AutoML. This is new functionality that originates from Oracle Labs to increase model quality and data scientist productivity, reducing overall compute time whenever possible. Machine learning techniques are actually employed to provide these automated capabilities. We introduced three functions, one for feature selection, model selection, and hyperparameter tuning. With auto feature selection, we reduce the number of features by identifying those most relevant to predict a target. This can result for both improving execution performance and model accuracy. With auto model selection for classification and regression, we want to identify the best algorithm to achieve a maximum score, and do this faster than if we had to exhaustively search through all the algorithms. With auto tuning of hyperparameters, the goal is to significantly improve model accuracy through selecting the best hyperparameters, but avoid manual or exhaustive search techniques, which are both costly in terms of time and resources. To illustrate automated feature selection, there are many real-world data sets that have a large number of relevant features. These can slow down training, but may also reduce accuracy. We tested a wide range of OpenML datasets, and here is one for dataset 312 that has about 1,900 rows and shows that we can reduce the model training time by a factor of 33 while increasing prediction accuracy by 4%. In a more dramatic case, we have another dataset with 56,000 rows and 784 columns, where we reduce the number of columns by half and even more significantly improved accuracy while reducing training time by a factor of 1.3. Looking more broadly at 150 datasets from the OpenML dataset suite that have more than 500 cases, we see some of the dramatic improvements in accuracy while reducing the number of features around half. Here, for the support vector machine Gaussian model. To invoke auto feature selection, we create a feature selection object, indicate the mining function, whether classification or regression, and select a scoring metric. In this case, we're selecting accuracy. We then invoke the reduce function on our feature selection object and specify an algorithm and our training data. With the selected features, we can then reduce the training set. The invocation for automatic model selection is similar. We create a model selection object and then invoke select on it, providing the training data. The return selected best model can be used for prediction. To invoke automatic hyperparameter tuning, we create an auto-tune object, again specifying the mining function and scoring metric. We then invoke tune on that auto-tune object. We can extract the best model and use that to make predictions. Here are some results for auto-tune involving the in-database neural network algorithm. run against a variety of datasets, around 300, the average improvement in accuracy was around 1.6%, while some datasets saw as much as 8 or 24% improvement. Even for the modest average gain, in certain applications, this can be a huge advantage. Before we wrap up, let's take a look at possible deployment architecture or usage scenarios with Oracle Machine Learning for Python. We see on the bottom right that we have Oracle Database with Python 3 engine installed, along with Oracle Advanced Analytics and the server components of Oracle Machine Learning for Python. Installing OML4Py enables the Python script repository and Python object data store automatically. Users can connect direct from a Python client, perhaps from their laptop. Others may choose to use a Zeppelin or Jupyter-based notebook environment, providing a web interface to users. Still others may leverage dashboarding tools like Oracle Analytics Cloud, Oracle Data Visualization Desktop, Oracle Business Intelligence Enterprise Edition, of the SQL invocation of Python scripts through embedded Python execution. One added item is that data can reside on, say, the Big Data Appliance or Hadoop, and be accessed through Big Data SQL, because Big Data SQL makes such remote data appear as tables in the user schema. These tables can be referenced and manipulated with OML4Py. So, in summary, Oracle Machine Learning for Python enables users to leverage Oracle Database from the Python scripting language and environment. Oracle's Python technologies extend Python for enterprise use, which means data scientists and analysts can analyze more data, explore data faster, and perform scalable machine learning. Just as important is the ability to put Python scripts into production quickly and easily. With automated machine learning, key data science steps are streamlined for greater data scientist productivity while enhancing model accuracy and performance. All in all, Python users can now achieve performance and scalability by leveraging Oracle Database as a high-performance compute engine. Thank you for your interest in Oracle Advanced Analytics and the new Oracle Machine Learning for Python component.